This is a video on finding the minimum angle. The question states, a baseball is hit at 150 feet per second from a height of 3 feet towards an 8-foot fence that is 400 feet from home plate. Find the minimum angle required for a home run. And a home run means that we've hit it over that fence, so just at that fence 8 feet high. Assume gravity is the only force acting on the ball. So since gravity is the only force on the ball, that means the acceleration of gravity is the total acceleration. And the acceleration of gravity is negative 32 J. J is the up direction. So negative 32 means downwards. And I'm going to let I be the direction from home plate to the fence. So I'm given some initial conditions. I'm given that the baseball is hit at 150 feet per second. So we can say that v sub 0, we don't know the angle it's hit at right now. So we use polar coordinates. 150 is the magnitude of the velocity, kind of like the r. So v of 0 is equal to 150 cosine of theta, that's r cosine theta, I, plus 150 sine of theta, j. We also know that it's hit from a height of 3 feet. So that means the initial position is 3 feet above home plate, or that r of 0 is 3j. We also know that when the ball is at the fence, I'm going to call that t final, or t sub f. We're 8 feet high and 40 feet from home plate. So this gives us that r of t final is equal to 400I plus 8j. So here's our acceleration, and we have these initial and final conditions. So to find the velocity given the acceleration, we integrate the acceleration. And the integral of negative 32j dt is, well, the integral of 0 is a constant. I'm going to call that v sub x I. And the integral of negative 32 is negative 32t plus a constant, which I call v sub y, and then times j. So now I can set our time is equal to 0, and we're supposed to get 150 cosine of theta I plus 150 sine of theta j. So that tells us that v sub x is 150 cosine of theta. And if we plug in 0 for the time for the j component, we get v sub y is 150 sine of theta. So we could say that v of t is 150 cosine of theta I plus negative 32t plus 150 sine of theta times j. So there's our velocity. To get the position function, we integrate the velocity. The integral of 150 cosine of theta I is 150 cosine of theta t plus a constant, which I call s sub x, times I. And the integral of negative 32t is negative 16t squared. And the integral of 150 sine of theta is 150 sine of theta times t. And then I still add a constant, which I call s sub y, times j. So that gives me my position function. We know that when time is 0, we get 3j. So I plug in 0 for t, and that tells us that s sub x should be 0 because the I component is 0 here. And if I plug in 0 for t for the j component, I just get s sub y is 3. So we could say that the position function is equal to 150 cosine of theta t times I plus negative 16t squared plus 150 sine of theta t plus 3 times j. So now let's use this t final condition. If we plug in t final, we're supposed to get 400i plus 8j. So if I plug in t final, here I get 150 cosine of theta times t final, and I set that equal to 400. If I plug in t final for the second component, or the j component, I get negative 16 t final squared plus 150 sine of theta times t final plus 3 is equal to 8. So I now have two equations and two unknowns in theta and t sub final, and I want to solve. So I divide by 150 cosine of theta for this first equation on both sides, and I get t final is equal to 40 over 15 times the cosine of theta. So I plug that in to the second equation to get that negative 16 times 40 over 15 cosine theta quantity squared plus 150 sine of theta times 40 over 15 cosine of theta plus 3 is equal to 8. So this is an equation in one variable that's very difficult to solve by hand. So instead, I actually used a computer, and I used a solver in a computer, and I got that theta was approximately equal to 0.316 radians. And that's the minimum angle required for a home run. And I'm done with the problem.